Hi and welcome to our video presentation of the Polimillionare contest notebook developed by Camilo, Andrés Martínez, Juan, Martín, Sánchez and Reinaldo Toledo.
Our architecture was implemented by focusing on a local execution pipeline. By utilizing open-weight models like Gemma and Juan, we utilized over 17 different architectures for what we call our council hardness. Due to the resource constraints of our testing environment, we focused mainly on 4 and 2 billion parameter models. The strategies we used to test our different hardness configurations focused on the VRAM constraints of our local environment and an iterative approach to tune that hardness. This led us to focus on a wide range of configurations from single model responses to quantized multi-agent systems that are both lightweight and can digest information in order to produce a reasonable answer.
To handle questions that require external knowledge, we built two main systems, retrieval and multi-agent reasoning. First, the RAG pipeline. When a question arrives, the system decides whether it needs external information. If it does, we perform a live web search using DuckDuckGo. Then we extract the content from the retrieved pages, clean it, and construct a context window that is injected into the model prompt. So instead of guessing at the end, the model answers using real evidence. The second part is the multi-agent council system. Here, instead of a single model, we run multiple local models in parallel, like Gemma and Queen. Each one produces its own answer independently, almost like different experts solving the same problem. Then we aggregate their outputs using a consensus mechanism, a voting step that selects or reconciles the final answer. This helps reducing hallucinations because one model can correct the mistakes of another. One practical issue we had with this was the memory usage, mainly because running multiple models in parallel can quickly exhaust GPU memory. So we added explicit cache clearing and cleanup after each inference cycle to keep the system stable.
To decide which strategies to actually use in the live game, we first ran a benchmark using theory-controlled equations across all 17 architectures. The results were quite consistent. The best performing setups were 4-bit RAG-based pipelines. For example, Gemma reached about 73% accuracy and Quen around 70%, while keeping response times between 7 and 9 seconds. On the other hand, more reasoning-heavy configuration performed worse in practice. They tend to slow the system down and sometimes even reduce accuracy due to strict formatting issues. We also saw that generating routines sometimes introduced latency spikes or timeouts. Based on these results, we built an automatic selection strategy that chooses the best architecture depending on the question category. Now in the live round, the strategy performed very well. We achieved perfect accuracy in categories like philosophy and psychology, correctly answering all questions and reaching over 1 million points in total. Finally, we extended the system to speech input. For this, we integrated whisper from transcription. This allows us to process spoken questions quickly, but it also introduces some noise. We observed that transcription errors, especially with names, numbers, and technical terms, can propagate into the model and affect reasoning quality. So overall, there is a clear trade-off. Adding speech improves usability, but slightly reduces accuracy due to input noise entering the pipeline.